Okay, to finish up this section, what I want to do is look a little bit at applying transformations to an example that we're going to be using over and over again, which is just a rotating cube. And next lecture we'll show how to use some modeling ideas to build up that cube. But let's assume we can do that, and what we're interested in now is using transformations to rotate it. So what we want to look at is a couple of different ways of doing that. And let's look at it for a second. I started off, let's see if I can get to it. Here we go. So here's the cube. It's got three buttons, pretty simple buttons, just as we did before when we were looking at chapter 3. You change it and change the direction of rotation. We're doing interpolation on the sides, but this cube started off being aligned with the x, y, and z axes, so you can think of this as sort of a changing instance transformation that's rotating it. It's centered at the origin, so in this example I don't want to worry about things like moving the fixed point around. So I'll come back later, we'll talk about how we add texture to this. We'll use it for various other purposes, but here I'm only interested in how we do the rotation, and as we see there'll be multiple ways of carrying it out. So let's start with this and let's look at how we can rotate it. And we have a lot of the issues that are the same as when we did the rotating square, when we said how do I animate this, and we had an angle theta, but there was only one angle then. Now we have three. Turns out that's not really the major issue. One of the major ones is where do we apply the rotation. Well, we looked at first at applying it in the application and just sending the vertices over and over again, rotating there, then getting new vertices in the new positions and sending them over to the GPU. And we decided that's really generally a bad idea because we're trying to not send data as over and over again to the GPU because that's the real bottleneck in the system. So we say, okay, let's do the rotation for this example in the vertex shader. Well, there are two distinct ways of doing that. One is I can compute a model view matrix each time we increment the angle and send over that model view matrix as a GL uniform matrix 4. The other way is to say, no, let's do everything in the shader and let's just send the angles over. And we looked at those strategies when we looked at the rotating cube, and they're pretty much the same, a little bit different here, and I think it's worthy of looking at them because I think it's not clear what the choice is between the second and the third strategy. Because in the first one, we do the trigonometry for all the vertices in the application, so we do it only once, but we're sending over more data. On the other hand, in the third case, we're actually sending only the angles over so that all the trigonometric calculations to form the rotation matrix are done in the shader. And I'm going to look at that shader in a minute. And it sounds like, gee, you're doing a lot of trigonometry because you're doing that for every vertex that comes along. And what if this is a more complex object? So that's what makes it a little unclear. However, in a modern GPU, those trig functions are kind of hardwired in. And they're not, you think, oh, a trig function, it's pretty complicated to take a sine or cosine. But in fact, it's not. It's very, very fast. So this is an area where you can very easily do some experimentation on one or more GPUs with a very simple program or my program and see what happens, because I think the results, I suspect, are going to be very unclear and are going to be very dependent on what GPU you have and what CPU you have. So let's look at the third option here and say, okay, what do I need in my vertex, in my application, and then in my vertex shader? In the application, I need to put some event listeners in so I could decide which angle I want to rotate about, which one I want to change. So let's say there's just a variable axis that starts off set to the x-axis. And then I have three event listeners that listen to those three buttons that I just showed you, and just says, well, if you get a click event from one of those buttons, then that decides which axis you're going to rotate about from then on. So you can have an array that has the value of theta for each of those axes, theta x, theta y, theta z, and depending on which axis it is, then in the render function, you increment that by, here we're incrementing it by 2 degrees each time we go through our standard render function that then recursively calls itself by request animation frame. So this is a pretty straightforward little way to do the interaction with this, but the part we want to focus on is, okay, I've sent the angles over. What do I have to do in that vertex shader? So let's look at a rotation shader done in a very sort of brute force kind of way. So what we're sending over is the position, we're sending over the color. We're going to interpolate the colors, so what we're going to do is we're going to just output the color as a varying variable. So this is all standard stuff that we've done before, and I'm going to take in the 3 angles. So theta here is a vec3, theta of theta x, theta y, theta z, that's going to come from the application and be changed within the render loop. Okay, so let's see what we can do. Well, I'm going to set 3 angles here. I have to convert to radians because the trig functions use radians, but GLSL has a radian, a degree to radian function built in, so we run through. Notice that these functions are all overloaded. So if this was a single variable, or 3 in this case, that it's overloaded, and what it does is produce 3 angles because I put in 3 thetas. Likewise, the trigonometric functions are overloaded, so that if I put in 3 angles and ask for the cosine, I get 3 cosines in a vec3. So it makes it for very nice, clean, short code. And now I have the sines and the cosines of all these angles, so I don't have to keep recomputing them. Saves me a little bit of work. And now what I'm going to do is compute a rotation matrix in the x direction, in the y direction, and in the z direction. So I specify a mat4, and here it is. Now notice, this is a little tricky, that's why we have this comment in here. Notice that all I'm doing is specifying 16 elements in a row, but these are interpreted as being column major because this is an OpenGL function, it's in the GLSL. So it's assuming that what I'm giving you is the first column, the second column, the third column, and that should agree with the signs that we had before. Now in this case, it's no big deal, because if I just reverse these signs, all it would do is rotate in the opposite direction, and it still looks basically the same. But if this were a translation matrix where we have the right row or the right column or the bottom row have the data, the dx, the dy, the dz, then the difference between a column major and a row major representation is clearly very important to us, and so that's just a little reminder. So there's the x rotation, here's the rest of the shader, here's the rotation about the y-axis, defined the same way, the rotation about the z-axis. Now we're essentially done. We send out the color that came in to be interpolated by the rasterizer, and we now say the new position is the position we sent in, because we're still using clip coordinates to just make these examples simple and clear. And now we do an x rotation, a y rotation, a z rotation. So if you look at this again, from what I said before, is you're computing in the vertex shader, you're computing the sines and the cosines about x, y, and z every time, and you're applying, and you're doing it for every vertex. Is that better than sending over the model view matrix, or the rotation matrix in this case, just once for each object? It's going to depend on a lot of things, and it's worth trying. But anyhow, here's a simple rotation shader that you can try, and this gets me into now looking at some more little problems that arise when you're doing rotation. And the problem is that issues arise when you do say, oh, a rotation matrix is based on the Euler angles. And the Euler angles say, oh, I'm going to rotate about x, then I'm going to rotate about y, then I'm going to rotate about z to get the desired rotation. If you're trying to do this in an animation, you have some potential problems that you have to deal with. And mostly they deal with trying to go smoothly from one position to another position. So think of it as trying to see that cube rotating smoothly, or if you're moving a camera along some path, you want that camera to move in a very smooth way, or the film or animation you produce is going to look very, very, very jerky. So you're applying a sequence of matrices, and obviously you want to do that efficiently. But to do this smoothly, then the issue is that what I'm doing is a little bit of X, a small, so to get it smooth, I'll do a small X rotation, small angle change, small change in Y, a small change in Z, then I'll go and do the same thing over and over again. So I do lots of rotations. If I try and make that change in X or Y or Z bigger, then I can actually notice, instead of really seemingly about rotating about in some angle about a certain axis, I actually notice I do is, oh, X, Y, Z, X, Y, Z. So on the average, I'm right, but I actually see the jerkiness of this motion because I'm using the Euler angles. So there are some alternatives to this, and I'll give a lecture on this a little bit later, maybe make it optional, but I certainly want all you graduate students and anybody who's taken 412 in the past to see it, where we look at some alternatives. And one is this idea that every rotation corresponds, about an arbitrary axis, corresponds to going around a great circle on a sphere. Remember, great circle is corresponds to having something that essentially like an equator, but rotated on that sphere. So it's sort of the maximum length circle that you can draw on the sphere. So now, can we use that? One way we can do that is to create what's called a virtual trackball, and I'll probably stick in a lecture about that at some point, but it's in the notes of the book. What that does is say, when I rotate a trackball, it gives me positions that I can interpret as being a couple of positions on a great circle that will define an axis of rotation and a smooth rotation. The other way is to try and do it incrementally, so that you get a sequence of rotations, whereas we said a minute or two ago, each of those is very small. It's not very efficient. We can do things, and again, this is in the notes somewhere. We can say, oh, why don't you not do trigonometric calculations? Why don't you use small angle approximations if you're doing very small increments, and use that cosine of 0 is approximately 1, and sine of a small angle theta is approximately equal to theta. Well, you can do that, and things really do speed up, but it turns out if you look at that sequence, in fact, you get errors accumulate as you're doing it, and you have to be very, very careful with that technique. The thing that's done in computer graphics a lot, especially in animation, it's also done a lot with aerospace, with airplanes, with satellites, is to use what's called quaternions, which turn out avoid that problem of using Euler angles. See, because it really arises because we said, oh, we're going to do Euler angles. They're simple to do, but they then lead to problems. It turns out quaternions avoid some problems, and I am going to stick in a lecture about this because it also has very interesting consequences, like what some of you may have heard of gimbal lock, and I want to talk about that. But just to tell you, to sort of finish up this lecture, is that what a quaternion is one way to look at it is an extension of imaginary numbers from 2 to 3 dimensions, and it was a problem that concerned mathematicians for a long time, because it turns out when you go from 2-dimensional problems to 3-dimensional problems, you need if you talk about the extension of imaginary numbers, you need 3 imaginary components, not 2. So a quaternion has what looks like a scalar plus 3 other scalars that multiply components I, J, and K, which correspond to imaginary numbers, in the sense that I times I is -1, and J times J is -1, and K times K is -1, but they're different from each other. We'll talk about that. But they turn out give you very smooth rotations because they do rotations on great circles on a sphere, and so they directly give you what you want. And it turns out it's fewer operations than using the Euler angles. So what people will do is they'll convert a model view matrix for rotation to a quaternion, do all of the operations with quaternions. Now it also turns out another very, very simple, nice exercise is to do a quaternion shader for rotation instead of doing this sort of Euler angle rotation. And it turns out a quaternion shader is just a couple of lines of code. It's a very, very beautiful little implementation of it. But then you go back from the quaternion world back to the model view matrix at the end by just putting the components that you computed in the right place. And as I said, I'll give you a lecture for that. Now, one final slide about what are the remaining problems, and just in general how you interactively use devices which we use all the time, like a mouse and a trackpad, to really work in 3 dimensions. So, I mean, how do you do a 3-dimensional rotation? If I were to control that cube not by pushing buttons, but rather by having some direct interface where I sort of click on the device and I move my mouse to get it to rotate what I want. Or if I start off with trying to form an instance matrix, so I put say a cube, a prototype cube, aligned with the axes of size, centered at the origin with maybe a side of length 1 or 2. How do I get that to be what I want it to be? How do I get it in the orientation I want, at the size I want, and put it somewhere with a device like just a mouse? So we could look at that. One way is to look at the virtual trackball, which as I said, I'll stick in a lecture somewhere about, but it's in the notes, or to use a more complex device. But the complex devices are problematic in the sense that we're not used to it. We're used to using a mouse, we're used to using a trackball and some other things, but when I give you a device that has 6 degrees of freedom that you can push, and twist is different than pushing, that's a problem. Probably the more fruitful area is to look at ways of using the display, whether it's putting a bunch of buttons or slide bars up on the display, or maybe having different areas on the display be used for different things. Maybe one part is used for scaling, one part's used for rotation. So it's a wide open thing, but that all falls in the realm of user interface design, and we're not going to really focus on that. But when you do your projects, you might want to think about these kinds of issues.